Quiet Science Journeys. These videos are designed to let your mind drift through calm cosmic stories, whether you stay awake listening or slowly fall asleep. Tonight, imagine a dark field filled with quiet points of light. Not stars close to home, not planets with familiar motion, but distant galaxies scattered gently across a wide map. Each point feels fixed at first, as if the sky were a surface you could measure once and trust forever. From far away, the scene feels stable. Nothing appears to stretch or shift while you're looking. The space between points seems settled complete, as if distance were a permanent feature of the universe. A ruler feels like one of the simplest tools we know, a straight line that turns separation into a number and gives space a sense of reliability. In everyday life, that reliability feels unquestionable. A road does not change its length while you walk along it. The distance between two buildings remains the same whether you look today or tomorrow. On human scales, space behaves as if it were fixed a background that does not participate in time. Because of that, distance feels independent. It feels like something that exists on its own while time moves separately through it. We measure space and then we measure change as if they belong to different categories. For most purposes, that intuition works. It allows cities to be built, maps to be drawn, and journeys to be planned without hesitation. The world feels steady enough that the ruler rarely fails us. But when we turn our attention outward, that intuition begins to soften. Light from distant galaxies does not arrive immediately. It travels for millions, sometimes billions of years before reaching us. During that travel, the universe does not remain still. Space itself expands slowly and continuously, while the light is already on its way. The background stretches even as the signal is moving across it. This means that distance does not behave like a static gap. The separation between where the light began and where it is received changes during the journey. Distance gains a history. Every observation arrives late. Not late by accident, but late by necessity because travel time is built into the act of seeing. A distant galaxy is not a distant object in the present moment. It is an earlier version of the universe delivered to us by the time it took its light to cross an expanding space. The farther we look, the deeper into the past we see, not because the universe stores images, but because light carries time with it. This effect is not subtle. It is written directly into the light itself. The farther a galaxy is, the more its light is stretched, its wavelengths pulled longer by the expansion of space. That stretching is called redshift. It is not only a sign of motion through space, it is a sign that space has been changing while the light was in transit. The sky then is not a picture of one moment, it is layered. Nearby galaxies show a recent universe while distant ones show much earlier chapters stacked together in the same field of view. Seen this way, the quiet map of points begins to feel different. Each dot carries not only a position, but a time. Distance and history become inseparable. This is where the simple ruler begins to struggle. A ruler assumes that space stays put while measurement happens. In an expanding universe, that assumption quietly fails. So a different question takes shape. How do you measure distance when distance itself has been changing? How do you assign a number to separation when the background has been stretching the entire time light was traveling? Cosmology answers this question without urgency, not by chasing objects and not by watching events unfold, but by looking for patterns that persist. Patterns that remain readable even as the universe grows. The journey ahead follows three calm steps. First, how surveys turn the sky into layered maps where position and time are recorded together. Then, how an ancient wave left behind a preferred scale written into matter long before galaxies formed. And finally, how that fixed scale becomes a ruler for expansion itself. A ruler that does not change length even as the universe around it grows. A ruler that allows distance to be read as history. For now, stay with the opening image. A quiet field of galaxies evenly scattered, calm and unremarkable at first glance. And a ruler in your hand, familiar and straight, ready to measure. The ruler will not change, but the meaning of what it measures will. As the light continues, its long journey across an expanding universe space keeps growing beneath it. Distance becomes more than separation. It becomes a record of time, and that record is already waiting in the sky. Surveys do not guess this, they measure it by comparing millions of galaxies across the sky. A telescope does not simply show objects. It collects light, and light always arrives late. Even nearby galaxies are seen as they were in the past. The delay may be small on cosmic terms, thousands or millions of years, but it is never zero. For distant galaxies, the delay stretches into billions of years, long enough that the universe itself changes while the light is still travelling. This delay is not a flaw in observation. It is a built-in feature of how seeing works. Every photon carries a departure time as well as a direction. When a telescope gathers that light, it gathers history along with position. The sky does not offer a single moment frozen in place. It offers layers. A galaxy survey is designed to organize those layers. Its goal is not a dramatic picture. It is a careful arrangement of information where location and time are recorded together. Each galaxy in a survey is given two basic labels: a position on the sky and a shift in its light. Together, these labels turn points of light into entries in a map that extends across time. The shift in the light is subtle but persistent. Spectral lines appear slightly stretched their wavelengths longer than when they were emitted. This stretching is called redshift. Redshift is often described as motion, but in cosmology it carries a deeper meaning. It reflects the expansion of space itself while the light is in transit. As the universe expands, the background through which light moves grows. The wave does not fight this growth. It is carried along, lengthened by the stretching of space. Because of this, redshift functions as a time label. Higher redshift means the light began its journey earlier when the universe was younger and smaller. Lower redshift means the light was emitted more recently. When sky position and redshift are combined, the survey becomes three-dimensional. Not a snapshot of space at one instant, but a structure that spans different epochs. Moving through the map is like stepping backward through cosmic time. One galaxy by itself does not reveal much. Its distance can be affected by local motion, and its surroundings can be unusual. Meaning appears only when many galaxies are considered together. As surveys grow, patterns begin to emerge. Dense regions where galaxies cluster, long filaments stretching across space, wide gaps where matter is sparse. This arrangement is known as the cosmic web. It is not a decoration added afterward. It is the result of gravity shaping matter over billions of years inside an expanding universe. At first glance, the web looks irregular. Clusters vary in size, filaments twist and branch. But beneath that complexity, something quieter is present. A preference. A separation that appears slightly more often than others when galaxy pairs are counted across the survey. This separation does not announce itself visually. You cannot draw a circle around it in the sky. It emerges only through statistics by counting how often galaxies appear at different distances from one another. Most separations behave smoothly. They follow a broad distribution shaped by gravity and expansion. But one distance stands out just enough to matter. The excess is small, it would disappear in a small sample, but in large surveys it persists. The same separation appears again and again, across different regions of the sky, across different surveys built with different instruments. Persistence is important here. In cosmology, repetition is a form of evidence. Patterns that survive scale and method earn attention. This preferred separation does not belong to any single galaxy. It is not tied to brightness, shape, or type. It belongs to the distribution as a whole. Seen this way, distance begins to change meaning. It is no longer just a number between two objects. It becomes a comparison across time. Each measurement of the separation is made at a different redshift. The separation itself does not change, but the universe around it has expanded by different amounts. So the apparent size of the separation becomes a record of how much space has grown between the time the light was emitted and the time it was received. Distance turns into a timestamp. This is why galaxy surveys matter. They do not simply catalogue objects, they organise history. By laying these maps side by side, cosmologists compare the same scale across different epochs. They watch how the background changes while the ruler remains the same. Geometry begins to tell a story. Nothing about this process is hurried. The signal is weak and it emerges only when noise is allowed to fade. Large volumes matter more than sharp images. There is a discipline to this approach. Rather than focusing on individual galaxies, attention shifts to relationships. Spacing becomes more important than appearance. The sky, once seen as a flat dome, becomes layered. Near and far are no longer just directions, they are positions in time. A survey map holds all of this quietly. Points of light, each one carrying a history. Distances that mean different things depending on when the light began its journey. This prepares the ground for a deeper question. If a preferred separation exists across cosmic time, something must have set it early. Before the web, before galaxies. So the map remains on the screen, the clusters and filaments stay in place, and the journey moves backward toward a younger universe. A time when matter and light were still tightly bound together. A time when a simple wave could travel outward and leave a mark that would survive for billions of years. That mark is the scale the surveys are quietly revealing. The ruler that does not appear in any single image. The ruler that becomes visible only through patience. And that is where the story turns next. To understand why a preferred separation exists at all, it helps to step back beyond galaxies, beyond stars, beyond atoms. In the earlier universe, the sky would not have looked like a black field with points. It would have looked like a bright hot fog, thick with light and matter mixed together so tightly that neither could travel far without meeting the other. This is hard to picture from modern experience. In ordinary air, light moves freely. In the early universe, light did not. Photons were everywhere, but they were constantly scattered. Electrons with free nuclei were present, and the whole medium behaved like a fluid, not because it was calm, but because interactions were so frequent that matter and radiation moved together as one system. In that system, two forces mattered most. Gravity pulled inward wherever density was slightly higher than average. Pressure pushed outward because photons carry momentum and resist compression. Even a small extra density was enough to begin the competition. If a region contained a little more matter than its surroundings, gravity tugged it inward. But as it compressed, pressure built, and that pressure pushed back. This does not sound like a wave yet. But a wave is exactly what emerges when you have a restoring force. Gravity pulls, pressure resists, and the result is an oscillation. In the early universe, those oscillations were real physical motions of the plasma. They were not sound in air. They were acoustic waves in a cosmic medium, pressure waves travelling through a hot mixture of ordinary matter and radiation. A simple way to imagine the beginning is to picture a tiny overdensity, a slight excess of matter in one region. Gravity begins to pull material inward. Radiation pressure pushes outward. The push outward does not erase the overdensity. It sends a compression wave moving away from the centre, a ripple. That ripple travels through the plasma, spreading outward as time passes. It carries a pattern, a preferred distance from the starting point, the radius the wavefront has reached after a certain amount of time. This outward travelling wave is the origin of the standard ruler. Not as a ruler yet, but as a moving boundary, a growing circle of influence in the early universe. The wave did not travel at the speed of light. It travelled at the sound speed of the plasma, a speed set by the balance between radiation pressure and the inertia of matter. The details matter, but the meaning is simple. The early universe had a characteristic speed for these waves, and the wavefront expanded outward accordingly. While this was happening, the universe itself was expanding. The background was stretching even in those early times, but the wavefront still advanced, pushing outward through this coupled fluid, leaving behind a pattern in the distribution of matter and radiation. Then, after hundreds of thousands of years, the universe reached a turning point. Temperature dropped. Electrons began to combine with nuclei. Neutral atoms formed. And when electrons were no longer freely available to scatter photons, light could finally travel long distances without constant interruption. This transition is called recombination, and the moment light began to stream freely is often described as decoupling. The names are technical, the physical picture is clear. Before this moment, photons were trapped in the fluid, constantly pushing and being pushed. After this moment, photons began to free stream across space. When photons left the fluid, pressure support changed. The radiation pressure that had been driving the wave could no longer act in the same way on the matter. The wave was no longer sustained as an active moving oscillation. It did not vanish. It simply stopped travelling outward as a pressure-driven feature. By that time, the wavefront had reached a particular radius, not a perfectly sharp boundary, but a characteristic distance. a maximum reach set by how far the sound wave could travel before decoupling. This distance is the sound horizon. It is a scale with a clear physical meaning. The comoving distance a sound wave could propagate in the early plasma before the universe changed phase. The phrase comoving is a way of keeping track of expansion. It means we measure the scale in coordinates that expand with the universe so the ruler remains comparable across time. The details can wait. The key point is that the early universe set a preferred scale, and that scale can be expressed in a form that stays meaningful even as space grows. At the moment of decoupling, two things were left behind. First, the photons that were released formed a background of light that still fills the universe today, the cosmic microwave background. Second, the matter retained the imprint of the wave. Matter near the center had been pulled inward by gravity. Matter near the wavefront had been pushed outward and slightly enhanced at that radius. The wave left a subtle preference for matter to be found at a particular separation from the original overdensity. This is the core of the BAO imprint, a slight excess of matter at the sound horizon scale surrounding regions that began as overdensities in the early plasma. At the time, nothing looked like galaxies, but the pattern existed. A faint statistical structure in the distribution of matter created by a wave that had travelled and then stopped. Over the next billions of years, everything became more complex. The universe expanded, matter cooled. Gravity began to dominate structure formation on many scales. Small overdensities grew, gas collapsed into dark matter potential wells, stars formed, galaxies assembled, clusters and filaments emerged, and the cosmic web took shape. All of this is messy on small scales filled with nonlinear growth mergers, feedback, and local detail, yet the sound horizon imprint survived. Not as a visible shell around each galaxy, but as a statistical preference across the full distribution. The universe carried the early wave forward the way a fabric can carry a faint weave pattern, even after it has been folded, stretched, and handled for a long time. The reason it survives is tied to its size. The BAO scale is large, far larger than the internal physics of a single galaxy. Processes that complicate small scales tend to average out on such large separations. That does not mean the imprint is perfectly preserved. Nonlinear growth blurs it. Large-scale flows smear the sharpness of the feature, but the peak remains in the statistics, a gentle bump in the probability of finding pairs at that separation. The signal is weakened, not erased. This is why the ruler can be predicted and then recovered. The physics that sets the sound horizon is well understood. It depends on conditions in the early universe that are constrained by multiple observations, especially the cosmic microwave background. In practice, the early universe acts like a calibration lab. The CMB tells us about the contents of the universe at that time, how much ordinary matter, how much dark matter, how much radiation. From that, the sound horizon scale can be calculated. Then later, surveys look for the same scale in the distribution of galaxies. Not by seeing a ring, but by seeing a preference, a repetition. When the preference appears where the early universe predicts it should appear, the ruler earns its name. It becomes a standard ruler. There is a quiet elegance in this. A moving wave in a hot plasma becomes a fixed scale. A fixed scale becomes an imprint in matter. An imprint in matter becomes a tool for measuring expansion. The wave itself is long gone, the plasma is gone, but the pattern remains. A fossil is often imagined as a shape in stone. Here the fossil is a separation in statistics, a memory stored in the distances between galaxies across the sky. This is the sound horizon. Not a horizon you can point to in an image. A horizon in the sense of a limit the farthest reach of an early universe wave before conditions changed. The next step is to see how this faint imprint becomes measurable at all, how surveys turn millions of galaxies into one dataset, how a gentle preference becomes a peak, and how that peak is read as geometry. The map returns, the points of light remain quiet, and somewhere inside their separations the early universe is still present, repeating the same scale softly across time. The sound horizon does not announce itself in the sky. There is no circle you can point to, no shell glowing faintly around each galaxy. If you look at a single galaxy, nothing about it suggests a ruler. It is just one object sitting in one place shaped by its own local history. The imprint of the early universe is not written into individual galaxies. It is written into relationships. To find it, cosmologists stop looking at objects one by one. They begin looking at separations, how far galaxies are from one another across the survey as a whole. This shift in attention matters. Instead of asking what a galaxy looks like, the question becomes how galaxies are spaced. Distance becomes the object of study. In practice, this means treating a survey as one dataset. Every galaxy is paired with every other galaxy, not a few selected pairs, but all of them. The result is a vast collection of separations. Millions of galaxies produce trillions of pairs. Most of these separations are unremarkable. They form a smooth background, a broad distribution shaped by gravity expansion and the overall density of matter. At first glance, there is nothing special to see. The BAO signal does not stand out sharply. It does not dominate the statistics. It appears as a small excess, a gentle preference at one particular scale. This excess is sometimes called a bump. The word is misleading if taken too literally. It is not a dramatic feature. It is subtle, a slight rise above what would otherwise be a smooth curve, easy to miss if you do not know where to look. This is why size matters. In small surveys, the bump is lost in noise. Random clustering overwhelms it. But as surveys grow larger, something changes. The random variations begin to cancel out. What remains is what repeats, and the same scale repeats, again and again, across different regions of the sky. This repetition is what turns a hint into a signal. In cosmology, persistence is persuasive. A feature that survives averaging earns attention. There are different ways to reveal this preference. Some analyses work directly with the distances between galaxy pairs. They ask how likely it is to find pairs at each separation. Other analyses transform the data. They move from real space to frequency space. Instead of distances, they examine oscillations in a power spectrum. The mathematics differs, the language differs, but the physical meaning does not. Both approaches are looking for the same thing, a preferred scale, a memory of the sound horizon preserved in the distribution of matter. What matters is not the technique. What matters is agreement. The same scale appears no matter how the data is examined. This agreement builds confidence slowly, not through a single dramatic detection, but through accumulation. Different surveys, different instruments, different analysis pipelines. The same separation keeps appearing. This is how the BAO ruler earns trust, not because it is large or obvious, but because it is stubborn. The signal does not depend on galaxy type. Bright galaxies show it, faint galaxies show it. It does not vanish when surveys change shape. It does not shift when methods are refined. It stays where the early universe predicts it should be. Seen this way, the ruler is not imposed on the data. It is recovered from the data, predicted first, then found. This order matters. The physical length of the sound horizon is calculated from early universe physics. Only afterward do surveys search for it in the late universe, when the scale appears where it should geometry and history align. The early universe and the present universe speak the same language. Distance becomes a bridge between them. Still, the signal remains quiet. It never overwhelms the statistics. It sits there gently, requiring patience to notice. This quietness shapes how the ruler is used. It encourages caution. It rewards careful treatment of uncertainty. Each detection of the BAO signal comes with error bars, not because the physics is uncertain, but because the universe is finite. We can only observe a limited volume. Cosmic variance matters. One region of the universe is not identical to another. Large-scale features are especially sensitive to this limitation. That is why independent surveys are important. They provide independent samples of the universe. Agreement across them strengthens confidence. When two surveys see the same scale, it matters. When many surveys see it, it matters more. Repetition turns geometry into evidence. The BAO signal also changes with time in a specific way. The physical ruler does not change, but its apparent size does. At low redshift, the ruler appears more stretched. The universe has had more time to expand. The same physical separation spans a larger observed distance. At higher redshift, the ruler appears more compact. Less expansion has accumulated. The geometry reflects an earlier stage of growth. This is where the ruler becomes useful. Each measurement captures a moment, not a moment in the sense of an event, but a moment in geometry. Distance stops being a static quantity. It becomes a timestamp, a record of how large the universe had grown by the time the light was emitted. The ruler itself remains silent about causes. It does not explain why expansion behaves as it does. It only records how it behaves. This restraint is important. It keeps interpretation separate from measurement. It allows the ruler to function as a neutral reference. The BAO signal does not care about theories. It does not respond to expectations. It appears where the data places it. Because of this, BAO measurements are often described as clean, not because they are easy, but because they are geometric. They depend weakly on the complicated physics of galaxy formation. Feedback mergers and star formation shape small scales. The BAO scale sits above that complexity. This separation of scales protects the ruler. Small-scale messiness averages out. Large-scale structure preserves the imprint. The signal is not perfectly sharp. Gravity blurs it over time. Large-scale flows smear the peak. But even blurred, the scale remains recoverable. Techniques exist to sharpen it statistically, not by inventing information but by undoing some of the smearing. These techniques matter later. For now, what matters is that the signal exists at all. A wave that stopped billions of years ago still leaves a mark. That mark is not loud. It does not demand attention. It waits to be noticed. When cosmologists speak of reading the expansion history, this is what they mean. They are not watching galaxies move. They are comparing the same ruler across time. Each comparison adds a point. Each point belongs to a different redshift. Together they form a sequence. This sequence is not dramatic. It does not jump or oscillate wildly. It traces a smooth change. That smoothness is itself a statement. Expansion does not lurch. It evolves steadily. The BAO signal allows this to be seen without watching anything unfold. Geometry carries the information. Statistics reveal it. The ruler does not explain the universe. It constrains it. It limits what expansion histories are possible. This is enough to make it powerful, not as a final answer, but as a backbone. The sky does not advertise this backbone. It hides it inside vast datasets. It asks for patience. Millions of galaxies, trillions of pairs, a small excess that refuses to disappear. That refusal is the signal. The early universe set a scale. The late universe repeats it. Surveys reveal the repetition, and from that repetition distance begins to speak. The next step is to listen more carefully, to place these measurements in order, to see how the ruler traces expansion across time. The map remains open, the points stay quiet, and the same separation waits to be read again at a different redshift under a different sky. If you enjoy slow observation-based journeys like this, consider subscribing. These episodes follow how cosmic measurements are made and what they quietly reveal using real survey data and careful explanations. Now with the signal in place, we can begin reading the expansion diary across time. At first, the detection feels like a confirmation, a quiet proof that a preferred scale exists. But after the first confirmation, the ruler becomes something else. It becomes repeatable. A standard ruler matters most when it can be read more than once. Not only here, not only nearby, but across different times, across redshift. Each BAO measurement is tied to a slice of the universe, a range of redshifts, a range of look-back times. In one slice, the galaxies belong to a relatively recent universe. In another, they belong to a younger universe one step earlier. The ruler is the same physical length in every slice. What changes is the universe around it. This is the quiet heart of the method. A fixed scale viewed through different amounts of accumulated expansion becomes a record written in geometry. It helps to keep the image simple. Imagine the ruler as a length you trust, not because it is convenient, but because its length is set by early universe physics and anchored by independent observations. Then imagine placing that ruler down again and again at different redshifts. You do not move the ruler, you move the page. Each page is a time slice. Each page contains a measurement of how large that ruler appears in the sky and along the line of sight. From that, cosmologists infer cosmic distance at that redshift. One measurement is an entry. Many measurements become a diary. The diary is not filled with events, it is filled with spacings. The entries are distances paired with redshifts, each one belonging to a different era. At first, this can look like bookkeeping, numbers arranged in a table, points arranged on a plot. But the meaning is deeper. In an expanding universe, distance is never only spatial. It is tied to when the light began its journey, so each entry carries time as well as length. The ruler turns a survey into a timeline, not a timeline of moments but a timeline of geometry. There are two geometric directions hidden inside BAO measurements, across the sky and along the line of sight. Across the sky, the BAO scale appears as an angular separation. The same physical ruler projected onto the sky becomes an angle that depends on distance. Farther distances make the ruler appear smaller in angle. Along the line of sight, the BAO scale appears through redshift separation. A small interval in redshift corresponds to a distance, but the conversion depends on the expansion rate at that time. The same physical ruler becomes a way of measuring how redshift maps onto distance. These are two different views of the same idea: transverse and radial, angle and redshift. In many surveys, the information is combined. Sometimes the measurement is expressed as a single effective distance. Sometimes it is separated into these two components. The details depend on data quality and survey design. The meaning remains steady. The ruler is being used to measure distance as a function of redshift. This function is the expansion diary. Once the diary has multiple entries, cosmologists begin to trace a curve. Not a curve of objects moving, a curve of how distance grows with redshift. Behind that curve is the expansion of the universe itself. Space grows. The mapping between redshift and distance changes. The diary captures that mapping without asking why it changes. It records the shape of the history. It does not assign causes. This restraint is one reason the method is trusted. It stays close to observation. It does not require a story about what drives expansion in order to measure expansion. If you picture the diary as a path, each BAO measurement is a stepping stone, one stone at low redshift, another at a higher redshift. The stones do not sit evenly spaced. Some redshift ranges are easier to measure than others. Some surveys have more coverage in certain eras. Even so, the path has a direction, from the nearby universe toward earlier times, from larger accumulated expansion towards smaller accumulated expansion. At low redshift, the ruler appears more stretched in the observed distribution. The universe has had more time to expand since the early imprint was set. The same physical scale spans a larger distance in today's coordinates. At higher redshift, the ruler appears less stretched. You're observing an earlier universe. There has been less time for expansion to accumulate between then and now. Each entry says the same kind of thing. At this redshift, the preferred separation appears at this observed scale. From that, geometry implies a distance. Place these entries in order and a pattern forms, not jagged, smooth. This smoothness is not imposed. It reflects the nature of expansion itself. Space does not grow in bursts. It stretches steadily. The ruler traces that steady growth. From the curve, cosmologists often summarize the history in terms of an expansion rate. There is a function that describes how fast the universe was expanding at different times. The name can be saved for later. What matters is the idea. Repeated measurements of the same ruler reveal how the geometry changes across time. The diary becomes a way of turning spacing into a history. At earlier epochs, the universe's behavior was dominated by radiation and matter. Later, the balance shifted. The expansion history changed pace. The ruler does not explain these phases. It records them. It places constraints on how the curve can bend. If a model predicts a distance redshift relation that does not match the diary, the model struggles. No amount of elegance can rescue it. The geometry has to agree with the sky. This is why BAO has become central. It provides a clean target, a measured curve that theories must reproduce. The diary is also valuable because it connects different regimes of observation. The cosmic microwave background anchors the early universe and helps fix the physical length of the ruler. BAO measures the middle chapters, where the universe is mature enough to form galaxies but still far enough to reveal long trends. Other probes measure late times in different ways. Supernovae trace distances through brightness. Lensing traces how structure grows. bow sits among them as a geometric reference, not replacing the others, stitching the timeline. Seen this way, the diary is not a final chapter. It is a backbone. It holds the history together by insisting on one requirement. The mapping between redshift and distance must be consistent. There are limits to what the diary can do. Not every redshift range is equally well measured. Some eras remain quiet not because the ruler disappears, but because surveys have not yet mapped those pages well. But even with gaps, the existing entries already shape the range of what is plausible. They narrow possibilities. They reduce the space where speculation can hide. Progress here rarely looks like a sudden revelation. It looks like smaller error bars, sharper points on the curve. The ruler itself does not change. The measurements improve. The diary becomes clearer. This is an unusual kind of story. It is not driven by dramatic events. It is driven by repetition. The same scale appears in a younger universe and in an older one. The same preference returns in different maps. The same ruler keeps its length while the universe changes around it. Confidence accumulates in the same way, not through a single moment, through consistency across time and method. By the time the diary can be read as a curve distance has been transformed, it no longer feels like a static property of space. It feels like something that carries memory. The universe does not keep time with clocks in any direct way. It keeps time through relationships, through how scales appear when light moves through an expanding background. The diary is a record of those relationships. A set of entries written in redshift and distance. A curve drawn from repeated measurements of a ruler set long ago. And once that curve is in view, another question begins to form, not about whether expansion happened, but about how trustworthy each entry is, because a standard ruler is only useful if it remains honest. And in cosmology, honesty is earned through checks, so the next part turns toward that discipline. Survey limits, systematics, the quiet work that keeps the ruler reliable even as measurements become sharper and the pages of the diary grow more detailed. A standard ruler is only useful if it can be trusted. In cosmology, trust is never automatic. The universe is not a controlled laboratory, and observations arrive shaped by instruments, choices, and chance. Every galaxy survey begins with limits. It does not see everything that exists. It sees what passes thresholds of brightness, position, and observing time. Some galaxies are too faint to detect. Some lie behind dust or bright foreground stars. Others fall outside regions the telescope can cover efficiently. These gaps matter. If they are ignored, they can create patterns that do not belong to the universe. They can hide real signals or imitate them. The response is not to pretend the gaps are not there. It is to map them carefully. Surveys build detailed descriptions of where data is reliable and where it is not. This description is called a mask. A mask is not something that hides information. It is a record of trust. It marks regions of the sky by depth and completeness. It tells the analysis which areas contribute meaningfully to the measurement. Without a mask, statistics can confuse the shape of the instrument with the shape of the universe. Redshift introduces another layer of care. BAO relies on placing galaxies accurately in 3 dimensions. That requires redshift estimates that are precise enough to preserve large-scale structure. Some surveys measure redshift by resolving individual spectral lines. These measurements are precise. They also require time because each galaxy must be observed carefully. Other surveys estimate redshift from broad colors. They can map vast areas quickly. Their redshifts are less precise. Neither approach is wrong. Each trades precision for volume. What matters is that uncertainty is understood and included. If redshift errors are ignored, the ruler can appear blurred. The peak does not move, but it softens. Statistics lose sharpness. When uncertainty is modeled correctly, the signal remains usable. The ruler is weakened, not distorted. Honesty preserves meaning. The sky itself introduces variation. Atmospheric conditions change. Seeing varies from night to night. Detector sensitivity shifts across the field of view. Some regions are observed longer than others. These variations can change the apparent density of galaxies. Left untreated, such gradients can bias measurements. They can create false preferences or wash out real ones. Again, the response is modeling. Surveys track observing conditions alongside galaxies. They record depth, noise, and coverage. These records become part of the analysis. Beyond observation, there is a physical effect that cannot be removed. As the universe evolves, gravity pulls matter into denser regions. This nonlinear growth blurs the BAO imprint over time. The ruler does not vanish, but the peak becomes less sharp. Information is not lost, but it is spread. To address this, cosmologists use a method called reconstruction. The idea is simple in spirit. Large-scale flows moved matter from where it began. If those flows can be estimated, some of the smearing can be reversed. Not exactly, but enough to sharpen the signal. Reconstruction does not invent new data. It rearranges existing data statistically. The physical scale remains the same. After reconstruction, the BAO peak becomes clearer. Uncertainty shrinks. The ruler becomes easier to read. Even with all corrections, limits remain. Surveys cover a finite volume. They sample one universe, not many. This introduces cosmic variance. Large-scale features differ slightly from place to place. No survey can escape this completely. The solution is repetition. Independent surveys provide independent samples. Agreement across them builds confidence. If the same ruler appears in different maps, it matters. If different teams recover it with different methods, it matters more. Consistency replaces certainty. Simulations add another layer of trust. Cosmologists create synthetic universes with known properties. They populate them with galaxies and analyze them as if they were real. If the pipeline recovers the correct ruler, confidence grows. If it fails, the failure reveals where assumptions need revision. Testing becomes a form of listening. This process is slow. It does not produce dramatic announcements. It produces reliability. The BAO ruler is trusted not because it is elegant. It is trusted because it survives stress. Across instruments, surveys, and analysis choices, there is a fitting symmetry here. A ruler in a workshop is trusted because it is checked repeatedly. A cosmic ruler earns trust the same way. What emerges is calibrated confidence, not absolute certainty, a clear understanding of what the ruler can say and how precisely it can say it. This honesty matters. Without it, the expansion diary would drift toward interpretation. With it, the diary stays anchored to measurement. As surveys improve, the ruler does not change. The uncertainties shrink. Entries in the diary become sharper, not louder. Progress here looks like refinement. Error bars narrow, consistency deepens. The discipline behind this is easy to overlook. It rarely appears in headlines. Yet it is what allows geometry to speak with authority. Trust is not declared, it is built, quietly. Once the ruler has earned this level of trust, attention shifts, from how it is measured to what it can test, and just as importantly what it cannot decide. The diary becomes a reference, a structure that theories must respect, a boundary that speculation cannot cross without evidence. This restraint is part of the method. It keeps cosmology grounded. It allows progress without losing footing. The ruler does not demand belief. It invites verification, again and again. As measurements improve, the diary gains pages, not new stories, clearer ones. The sky remains patient, the ruler remains steady, and trust grows one careful correction at a time. The next step is not to ask more of the ruler than it can give. It is to ask how its quiet record fits among other measurements, how geometry joins brightness lensing and background light, because no single probe tells the whole story. Each adds a piece, and together they shape what the universe allows us to know. Once the expansion diary is in place, it can feel like a verdict, a curve drawn from measurements, a history traced in distance and redshift. It becomes tempting to look at that curve and declare that one explanation must be correct, that one ingredient must be responsible, that one model has won. Cosmology does not work that way, not when it is careful, not when it is honest about what geometry can and cannot tell us. The diary is powerful because it constrains expansion. It tells us how distances grow with redshift. It limits the set of histories the universe can have followed. But the diary does not uniquely determine the cause of expansion. Different physical ideas can sometimes produce very similar geometric curves. Geometry narrows the space of possibilities, but it does not always pick one possibility by itself. This is not a weakness of BAO. It is the nature of measurement. A ruler measures shape, not motive. Baryon says this is the distance redshift relation the sky supports. It does not say this is the only physics that could produce it. The diary records what happened to geometry, not why geometry changed that way. This distinction matters because it keeps observation separate from interpretation. It prevents the curve from becoming a story about destiny. It keeps the method grounded. Within the standard cosmological framework, BAO plays a clear role. It measures how the universe expanded through the middle chapters of its history. It anchors distances where other probes are less direct, but it operates inside a broad assumption that on large scales the universe can be described as a smooth expanding space-time. BAO does not test this framework from the outside. It measures within it. This is one reason cosmology relies on combinations of probes. Different methods depend on different assumptions. Different systematics shape their data in different ways. Agreement across them is reassuring in a scientific sense, not as comfort, as structure. The cosmic microwave background anchors the early universe. It fixes conditions when the universe was young, hot, and still simple in some ways. It also helps set the physical length of the BAO ruler through early universe physics. Baryon then measures the middle. It reads the same ruler across time, turning spacing into a history. It connects the early anchor to the later universe. Supernovae measure distance differently. They use brightness, comparing how bright an object appears to how bright it is expected to be. They trace the late universe with high precision over certain ranges. Weak gravitational lensing adds another perspective. It traces how matter bends light and how structure grows. It is sensitive not only to expansion, but to the way gravity builds the cosmic web. Each probe has strengths, each has limitations. None of them alone tells the full story. Together they cross-check one another. They limit the chance that a single assumption controls the conclusion. They build a picture that is harder to dismiss and harder to mistake. This is also where tension can appear. Sometimes different probes do not match perfectly. The curve drawn by one method may sit slightly away from the curve implied by another. It is important to treat such tensions with discipline. A mismatch is not automatically new physics. It is not automatically a mistake. It is a signal that deserves careful attention. Systematics can hide in unexpected places. Calibration issues can shift brightness. Selection effects can reshape samples. Modeling assumptions can differ. Priors can influence inference. Small choices can matter when precision becomes high. So the first response to tension is measurement. Improved data, better modeling. If a tension persists as measurements improve, it becomes more interesting. Not dramatic. Interesting in the quiet way science becomes interesting. Because persistent mismatch can mean one of two things: a shared systematic not yet recognized, or a missing piece in the model. Baryon plays a calm role in this process. Because it is geometric, it often provides stable reference points. It can help distinguish whether a mismatch is likely tied to distance calibration or to structure growth. It can also clarify what is and is not being tested. Some changes in physics alter expansion but not growth in the same way. Others alter growth more strongly than expansion. By placing Baryon alongside lensing and supernova cosmologists separate these influences. They ask whether the same model can fit geometry and growth at once. They look for consistency across the network. There are questions BAO cannot answer no matter how precise it becomes. It cannot tell you why there is something rather than nothing. It cannot tell you what happened before the earliest era we can model with confidence. It cannot decide whether spacetime is fundamental or emergent. Those questions live beyond the ruler's jurisdiction. A ruler measures within a space that already exists. Baryon also does not predict the far future by itself. It constrains the past and present pattern of expansion. It narrows possible futures by limiting model parameters. But it does not guarantee one outcome. Different models can fit present geometry yet diverge later. The diary is a record, not a prophecy. This is why the diary is best treated as a target. A clean geometric trace that any deeper theory must reproduce in the regime where data is strong. If a theory aims to describe our universe, it must pass through the measured curve. In that sense, BAO becomes a bridge. Not a bridge from ignorance to certainty, a bridge from observation to theory. It anchors what is real in the sky. It forces elegance to respect measurement. It keeps foundations tied to the world. This is a quiet kind of authority. The authority of repetition. The authority of constraint. The early universe set a scale. The late universe preserved it. Surveys recovered it. And from that recovery we gained a diary. Not complete, not final, but structured enough to say this is the shape expansion has taken so far. This is the geometry the universe permits. Whatever else we imagine, it must fit here. From this point, the journey can close in a simple way, by returning to the idea that began it, a ruler that seems ordinary, a straight line, a familiar tool. But in cosmology, the ruler does not only measure space, it measures how space has grown. It turns distance into memory. The diary remains open to new pages, new surveys, new measurements. The ruler remains the same, and the sky continues to offer its quiet pattern, waiting to be read with care. The journey began with something simple, a ruler, a straight line that feels familiar, reliable, and complete on human scales. In everyday life, the ruler does its job quietly. It measures roads, rooms, and distances that do not change while we look at them. It works because the space around us feels steady. The universe does not offer that same stillness. Light travels for billions of years. Space expands while the journey is still underway. And yet within that changing background, one scale remains, set early, carried forward. A sound wave moved through a hot, dense universe. It stopped when conditions changed. Its final reach became a length that did not disappear. That length was woven into matter, not as a visible mark, as a preference. Billions of years later, galaxies formed. They clustered, stretched into filaments, and filled space with structure. Through all of that complexity, the preference survived. Surveys did not see it at first glance. They found it by patience, by counting separations instead of objects. Again and again, the same scale appeared, in different maps, at different times. When that scale was measured across redshift, it became something more than a relic. It became a diary, a record of how space itself has grown. The diary does not tell a dramatic story. It does not rush. It traces a smooth curve built from repetition rather than surprise. Distance stops feeling like a static idea. It becomes memory, a number that belongs to an era, not just to space. The ruler never changes length. The universe around it does. That contrast is what makes the method work. The ruler does not explain why expansion behaves as it does. It does not claim to know the cause. It records the shape of history and leaves interpretation to follow. This restraint is part of its strength. It keeps measurement honest. It keeps speculation bounded. As new surveys arrive, the diary will gain pages, not louder ones, clearer ones. Error bars will shrink. Curves will sharpen. The ruler will continue to rest in the same place it always has. Above it all, the sky remains unchanged in its patience. Light continues to travel. Space continues to expand. The pattern is already there, waiting to be read again. Not as a single moment, as a steady trace across time. And that is enough. The ruler has done its work. The diary remains open, and the universe continues growing quietly, carrying its history in the spaces between things.